neighborhood of a point. Let X tau be a topological space. A subset Nx of X is called a neighborhood of X if there exists an open set G of tau such that X belongs to G and that G is subset of Nx. Next, we introduce the definition of limit point of a set. Let A be a non-empty set and non-empty set of a topological space X tau. An element small x belongs to capital X is called a limit point of A if every neighborhood of Nx of X meets A at a point other than X. Equivalently, we say that Nx intersection capital A minus of singleton X, it is equal to not equal to 5, and that small x may be belongs to outside the set capital A. For example 9, we get obtain the limit point if any of a set A, and that set is equal to 1, half, 1/3, 1/4 and so on. It is a well known set, and in this space R with respect to the topology, first hoche 1 usual topology, and next discrete topology, and finally indiscrete topology, and also cofinite topology. For the solution 1, let N0 be a neighborhood of 0. Then there is an open set or open interval AB such that 0 belongs to the open interval AB and that open interval subset of N0. From the definition of the neighborhood, we always get a open interval such that we satisfy this condition. Then this implies A strictly less than 0 and 0 strictly less than B. Then by the Archimedean property of R, we get a natural number k such that 0 strictly less than 1 by k and that is strictly less than B. So 1 by k plus 1 is strictly less than 1 by k because k plus 1 is also an integer and that k plus 1 is strictly greater than k. So 1 by k plus 1 is strictly less than 1 by k. Similar logic or similarly 1 by k plus 2 is strictly less than 1 by k plus 1 and 1 by k plus 3 is strictly less than 1 by k plus 2 and so on, and each elements of 1 by n or 1 by k plus 1, 1 by k plus 2, 1 by k plus 3 and so on, each elements all are positive because k is a natural number and 1 by k is strictly greater than 0. Then we get 1 by n belongs to open interval AB intersection A minus 0 and that is a subset of N0 intersection A minus singleton 0 for all n greater than or equal to k. That k we get from the Archimedean property that k we get Archimedean property k. So 0 is the limit point of A. Next, if we take x is equal to 1 by n for all n belongs to natural number, then we consider the open interval 1 by n minus 1 by n plus 1 and 1 by n plus 1 by n plus 1. That open interval intersection A minus 1 by n is always 5 since n plus 1 strictly less than n and that n strictly less than n plus 1 for all n belongs to natural number. From the picture it is obvious that the intersection is equal to 5. So x equal to 1 by n for all n belongs to natural number is not a limit point of A. Similarly, we can always get another points of R is not a limit point of A. And the condition 2, in this case, for the case 2, we consider the topology indiscrete topology. So tau is equal to power set of x. Let x belongs to real number. Then singleton x is a neighborhood of x. So singleton x intersection A minus singleton x, it is equal to 5. This implies x is not a limit point of A. So A has no limit point in R. For the condition 3, if we choose the topology that is discrete topology, then tau is equal to 5 comma R and R the set of a real number and choose x belongs to real number. Then only neighborhood of x is R. So only two possibility, phi or R, because phi contain no elements, so must be one possibility, x belongs to real number, that is only one neighborhood, that is R. So R intersection A minus singleton x, that is not equal to 5. This implies every point of R is a limit point of A. And finally, for the example 4, in the case we consider the cofinite topology, then tau is of the form phi union all such b such that b subset of real number such that R minus b is a finite set. Choose any point x belongs to real number and nx is a neighborhood of x, any neighborhood, nx is any neighborhood of x. Then R minus nx is equal to finite set from the condition of cofinite topology. So nx intersection a minus singleton x, it is equal not equal to phi. Since a minus singleton x is a infinite set and R minus nx is a finite set, so that intersection always not equal to phi. This implies every point of R is a limit point of A. Next we introduce the definition of closed set. A subset F of a topological space x tau is said to be closed if every limit point of F is a point of F. That means F contains all of its limit points just. Next, we introduce theorem 10. A subset F in x tau is closed if and only if x minus F is a open set in X. That means open, so x minus F belongs to tau. Now we introduce another very important notion, and that notion is called subspace topology or relative topology. A subset A of a topological space x tau and setting tau A is equal to A intersection U such that U belongs to tau. It is obvious that A tau A is a topological space and the pair A comma tau A is called subspace topology or relative topology of x comma tau. That is, x comma tau is the mother topology. We get an example. Example 11. Let x is equal to R. With respect to usual topology, we consider the set A is equal to close 0, open 1, union, open interval 3, 4. Then open interval minus 1, 2, intersection A, that is nothing but close 0, open 1. So from the subspace topology, close 0, open 1 is forms a open set, and similarly, why it is open? Because open interval minus 1, 2 is a open set in the usual topology, and similarly open interval 2, 5 is a open set, and that intersect A is equal to the open set 3, 4. So close interval close 0, open 1 and open interval 3, 4 both are open sets in A with respect to subspace topology. Similarly, since 0, 1 and 3, 4 both are open set, so its complement, that is A minus close 0, open 1, it is equal to 3, 4, and A minus open interval 3, 4 is equal to close 0, open 1. Both of them are open set, so its complement is closed set. That means 3, 4 is a closed open set, or 3, 4 as well as closed set. Similarly, here 3, 4 is open set, so that means their complement is closed set. So both sets of close 0, open 1 and open interval 3, 4 are open and closed set. So this is called closed set. Closed sets with respect to subspace topology. Next we define a continuous function over a topological space. A function f x tau x to y tau y is said to be a continuous function if for every open set u of y, f inverse y is an open set in X. For example, let us consider the projection mapping pi 1 from R square to R. R square means Cartesian product of R. We define pi 1 xy is equal to x, where x comma y belongs to R square. Let U be a open set in R. Then its inverse image under the projection mapping, that is pi 1 is equal to pi 1 inverse U, that is nothing but it is equal to U cross R, because pi 1 open U cross R, that is equal to U. So U cross R is a open set in R square. So pi inverse U is a open set in R square. This implies pi 1 is a continuous mapping. Similarly, if we choose another projection mapping pi to pi square R square to R, defined by pi 2 xy is equal to y, in similar logic we show that pi 2 is also forms a continuous function. we get another theorem. A function f x to y is continuous if and only if every closed set f in y, then f inverse y is a closed set in x. Proof is very simple. Let f be a continuous function. Since f is a closed set in y, so its complement in y, that is y minus f, is an open set in y. By using the definition of continuity, we get f inverse y minus f is a open set, and from the set property or function property, we get f inverse y minus f is equal to x minus f inverse f, and this is open set, so its complement, that means f inverse f is a closed set in x, and that's all. That means first part is obvious. Conversely, let every closed set f in y, then f inverse y is a closed set in x to prove that it is a continuous function. For this, we choose a open set u in y, then its complement in y, that is y minus u, is a closed set in y. By the using of hypothesis, we get f inverse y minus u, that is nothing but x minus f inverse u is a closed set, so f inverse u is a open set in x, hence the result. Next we get another example, and example 14. Let A be a non-empty subset of a topological space x, then the characteristic function chi a from x to r is continuous if and only if A is a closed set, that means A is both open and closed in x. Proof is very simple. Let chi a be a characteristic function of A. So chi a x is equal to 1 if x belongs to capital A, and it is equal to 0 if x does not belongs to A. Let G be any open set in R, then chi inverse G, that means inverse image of G under the characteristic function chi a, it is equal to x if G contains 0 and 1, and it is equal to A, capital A, if G contains 1 but not 0, and it is equal to x minus a if G contains 0 but not 1, and finally it is equal to 5 if G contains none of 0 and 1. Suppose chi x is a continuous function, so chi inverse, that is inverse image of G under the mapping of chi x, that is the characteristic function, is open set from the definition of a continuous function. So A and x minus a both are open set in x. This implies A is a closed set, because x minus a is open, so its complement A is closed, that means A is a open and closed in x. Conversely, let capital A is a closed set in x, then so that chi a such that x to capital R is a continuous function. Let G be a open set in R. Then above four sets means x, capital A, x minus a and phi, all are open set in x because A is a closed set, so A complement of A is also open, so x, a, x minus a and phi all are open sets in capital X. So chi a inverse G is open set, that this implies chi is a continuous function. Now we introduce two important maps. One is open mapping and another is closed mapping. Open mapping, a mapping f x to y is said to be open mapping if it sends open set into open set. That means O is a open in x, then f of O is a open in y. For closed mapping, a mapping f x to y is said to be a closed mapping if it sends closed sets into a closed set. That is, if f is a closed set in x, then small f, capital F, that is image of f under the mapping of small f, is closed in y. Next, we consider an example, that is example 15. Give the following examples: a continuous function that is neither open nor closed, and second one, a continuous function which is open but not closed, and finally give an example of a continuous function which is closed but not open. For first, we get, we consider an example, x is equal to singleton A, B, C. That means X, capital X consists of 3 elements A, B, C, and tau X is equal to phi, singleton A, doubleton AB, doubleton AC, and finally capital X. And Y is equal to consist of again 3 elements X, Y, Z, such that tau Y is equal to phi, singleton X, and doubleton YZ and Y. For first example, we define a function small f x to y such that f of a, f of b, f of c, all our element goes to small y. Let G be an open set in y tau y. Then inverse image of G under the mapping of f, that means f inverse G, it is equal to phi if G does not contains y, and it is equal to phi if G contains y. So it is obvious that f is a continuous function because phi and capital X both are open and closed also, and so f is a continuous function. Next, if we consider the set singleton f, if we consider the set singleton f, so image of f, image of A under the mapping f is equal to singleton y. Singleton A is a open set in X, but singleton Y is not a open set in capital Y. Singleton A is a open set in capital X because singleton A is a element of tau X, but singleton Y is not a open set in Y because it is not a element of tau Y, and it's also not a complement of any other set lies in tau Y. So f is not a open mapping. Again, f of singleton B, that is image of B under the mapping f, it is equal to singleton Y, and singleton B is a closed set in X since X minus AC is equal to B, and AC is a open set, so its complement B is a closed set, but singleton Y is not closed in Y, so f is not a open mapping. So it is an example of a continuous function which is open but not closed. Next we consider another example G from y to x such that gx, gy, gz, all our element goes to small a. Let u be a point in x tau x. Then G inverse u is again same as it is equal to phi if u does not contain a, and it is equal to y if u contains a. So G is a continuous function because phi and y both are open, so inverse image of open set is open, so G is a continuous function. Since G of phi is equal to phi and G of singleton x, G of yz and G of capital Y, all our element goes to singleton A, so G maps a open set into a open set. This shows that G is open mapping. Again G of singleton x is equal to A, and singleton x is a closed set in Y since y minus capital Y minus yz is equal to singleton x, and capital YZ is a open set in Y, but singleton A is not a closed set in Y, so f is not a closed mapping. Finally, for the example 3, we define a function small h y to capital X such that h goes to all element from y to c. Small c belongs to capital X, and we consider a open set in capital X tau x. Then h inverse u, that means inverse image of u under the mapping of h, is equal to phi if u does not contain c, and it is equal to y if u contains c. So h is a continuous function. Again h of phi is equal to phi, h of singleton x is equal to h of yz, and it is equal to h of y equal to a. So h maps a closed set into a closed set. This shows that h is a closed mapping. Again h of singleton x is equal to c, and singleton x is a open set in y, but singleton c is a closed set in x since x minus ab is equal to c, and ab, doubleton ab is a open set in x, so h is not a open mapping. That means h is an example of a continuous function which is neither open nor closed.